먼저 이번 포럼의 주최 기관인 한국경제신문 조일훈 사장님의 개회사가 있겠습니다. 자, 그럼 조일훈 사장님을 큰 박수와 함께 단상으로 모시도록 하겠습니다. 힘찬 박수로 환영해 주시기 바랍니다.
안녕하십니까 여러분, 반갑습니다. 한국경제신문 사장 조일훈입니다. 스트롱코리아 포럼 2026에 참석해 주신 여러분 대단히 환영합니다. 한국경제신문이 과학기술정보통신부와 공동으로 주최하는 스트롱코리아 포럼이 올해로 14번째를 맞이했습니다. 오랜 기간 포럼을 아껴주신 모든 분들에게 다시 한번 감사의 말씀을 드립니다. 특히 대한민국 과학기술 발전을 이끌고 계신 과학기술정보통신부의 유재명 제2차관님, 포럼을 주관해 주신 한국연구재단과 특허전략개발원 관계자 여러분 대단히 고맙습니다. 또한 오늘 축사를 맡아주신 황정아 의원님께도 깊이 감사의 말씀을 드립니다. 올해 포럼 주제는 피지컬 AI 모먼트, 반도체 변곡점입니다. 피지컬 AI와 첨단 반도체 기술이 산업 패러다임을 통째로 바꾸는 핵심 동력이 될 것이기 때문입니다. 세계 각국도 소브린 AI를 구축하고 반도체 패권을 거머쥐기에 사활을 건 전쟁을 벌이고 있습니다. 여러분들 모두 아시다시피 최첨단 반도체 강국인 우리 대한민국도 이런 변곡점에서 독자적인 피지컬 AI 생태계를 만들고 기술 강국의 위상을 더욱더 확고하게 다져야 할 시기입니다. 이를 위해 해결해야 될 과제가 적지 않습니다. 메모리뿐 아니라 차세대 AI 반도체 기술 확보, 로봇 모빌리티 산업과의 성공적인 융합, 6세대 신경망 구축 등이 모두 필수적입니다. 대전환의 길목에서 정부와 기업, 학계가 다시 한번 머리를 맞대고 지혜를 모아야 합니다. 오늘 포럼을 위해 국내의 최고 전문가분들을 모셨습니다. 기조연설을 맡아주신 딜런 테일러 보이저테크놀로지스 회장 겸 CEO님, 특별 강연을 맡아주신 김정옥 카이스트 교수님 감사합니다. 건인서 한국과학기술연구원 피지컬 AI 연구단장님, 박경 SK 하이닉스 부사장님께도 각별히 감사의 말씀을 드립니다. 오늘 포럼을 찾아주신 모든 분이 각 세션에서 유익한 정보를 얻어가시길 희망합니다. 한국경제신문은 대한민국이 피지컬 AI 시대를 선도할 수 있도록 사명감을 가지고 더욱더 열심히 포럼을 발전시켜 나가겠습니다. 다시 한번 참석해 주신 모든 분께 감사의 말씀을 드리며 여러분 일터와 가정에 늘 건강과 행운이 가득하기를 바랍니다. 감사합니다.
네, 감사합니다. 이렇게 또 뜻깊은 말씀으로 개회사를 해주신 조일훈 사장님께 다시 한번 감사 인사 드리면서 또 말씀 주신 것처럼 오늘 이 자리가 얼마나 큰 중요한 의미를 갖는지 다시 한번 생각해 볼 수 있는 귀중한 말씀이었습니다. 자, 이번에는 공동 주최기관인 과학기술정보통신부 류재명 제2차관님의 환영사가 있겠습니다. 자, 그럼 류재명 차관님을 단상으로 모시도록 하겠습니다. 큰 박수로 환영해 주시기 바랍니다.
예, 안녕하십니까. 과학기술정보통신부 제2차관 류재명입니다. 먼저 대한민국 과학기술의 미래 비전을 제시해온 스트롱코리아 포럼의 2026 행사에 함께해 주신 모든 분들을 환영합니다. 먼저 뜻깊은 자리를 마련해 주신 한국경제신문 조일훈 사장님께 감사드립니다. 그리고 의정활동으로 바쁘신 와중에도 이 자리를 빛내주신 국회 더불어민주당 황정아 의원님께도 감사의 말씀을 드립니다. 원래 국회의원분들 뒤에 정부 관계자가 축사나 이렇게 인사 말씀을 드리는 게 관례적인데요. 오늘은 이 과기정통부가 이렇게 주최기관으로 환영사를 하느라고 제가 먼저 이렇게 단상에 섰습니다. 그리고 기조연설을 해주실 딜런 테일러 보이저테크놀로지 회장님, 그리고 특별 강연을 맡아주실 김정호 한국과학기술원 교수님을 비롯하여 귀한 걸음을 해주신 국내의 석학과 산업계 리더 여러분께 거듭 감사의 말씀을 드립니다. 각계의 국내의 전문가와 리더들이 모여서 과학기술의 발전을 모색하는 스트롱코리아 포럼에서 이번에 피지컬 AI를 주제로 한 것은 시사하는 바가 매우 크다고 생각합니다. 이번 포럼의 주제처럼 지금 우리는 인공지능이 디지털 세계에만 머무는 것이 아니라 모니터 밖으로 나와서 현실의 물리적 공간으로 들어오는 피지컬 AI 모멘텀에 서 있습니다. 피지컬 AI가 전 세계적으로 주목받는 이유는 자율화를 실현하는 기술이기 때문입니다. 과거 기계나 로봇을 통해 반복적인 작업을 수행하는 자동화는 환경에 대한 엄격한 통제 없이는 실현이 불가능했지만 피지컬 AI가 가져올 변화는 자율화는 변칙적인 실생활 환경에서도 임무를 수행하여 할 수 있도록 할 것이기 때문입니다. 이를 통해 기존에 자동화되지 못하고 사람만 할 수 있었던 위험하거나 힘든 일들을 할 수 있는 단초가 마련되었습니다. 피지컬 AI는 제조뿐만 아니라 국방, 농업, 서비스 등 다양한 분야에서 대규모 혁신을 창출할 것으로 예상되며 이에 따라서 미국, 중국을 비롯한 선도국들도 피지컬 AI를 핵심 주권 기술로 국가 차원에서 투자를 하고 있습니다. 라지 랭귀지 모델 중심의 AI 경쟁에서는 우리가 다소 늦게 출발했습니다만 세계적으로 초기 단계인 피지컬 AI는 우리에게도 선두에 설 기회가 있습니다. 다행히 우리가 피지컬 AI를 선도할 수 있는 가능성과 잠재력을 갖고 있기 때문입니다. 최근 엔비디아의 젠슨 황 대표도 한국을 다녀가면서 대한민국 피지컬 AI 생태계의 역량을 높이 평가했던 것처럼 전 세계가 우리의 AI 역량, 산업 현장에서 축적해온 독보적인 경험과 노하우를 인정하고 있습니다. 과기정통부는 지금의 골든타임을 놓치지 않고 피지컬 AI 시대를 주도하기 위해 피지컬 AI 전략을 수립하고 지난달 과학기술관계장관회의를 통해서 관계부처와 함께 정책적 역량을 집중하고 있습니다. 특히 올해부터 국내를 대표하는 산학연이 힘을 모아서 우리 손으로 피지컬 AI 핵심 기술 개발에 착수하였습니다. 저도 지난 6월 9일에 있었던 사업 착수 보고회에 참석하여 우리 대학, 연구기관, 그리고 기업의 역량, 또 독자 기술을 확보하겠다는 열정과 의지를 확인할 수 있었습니다. 과기정통부는 월드 모델, 피지컬 AI 범용 파운데이션 모델 등 기반 기술 개발과 더불어 피지컬 AI 구현을 위해 무엇보다도 중요한 대량의 고품질 데이터를 빠르게 확보해 나가고 있습니다. 현실에서 데이터를 모으는 데는 너무나 많은 비용이 그리고 시간이 소요되기 때문에 현실 데이터 수집과 함께 월드 모델을 통해 대량의 합성 데이터도 확보할 계획입니다. 그리고 핵심 국산 기술을 바탕으로 대규모 실증을 추진하여 국민이 체감할 수 있는 가시적인 성과를 빠르게 창출하고자 합니다. 제조업 혁신을 넘어 국방, 가정, 돌봄, 농업 등 사회와 일상 전반으로 피지컬 AI를 확산시키겠습니다. 오늘 포럼에서 피지컬 AI의 경쟁력의 바탕이 되는 물리학부터 반도체, 소프트웨어, 네트워크에 이르는 주제들을 함께 고민하고 지혜를 모아주신다면 대한민국이 피지컬 AI를 선도하는 국가로 나아가야 할 방향을 찾을 수 있을 것이라 기대합니다. 정부는 여러분의 든든한 동반자로서 과학기술인과 기업인 여러분들이 마음껏 도전하고 혁신할 수 있도록 힘껏 지원하겠습니다. 다시 한번 오늘 포럼 개최를 위해 애써주신 모든 분들께 감사드리며 함께해 주신 여러분들의 건강과 행복을 기원합니다. 감사합니다.
네, 류재명 차관님의 환영사 말씀 다시 한번 감사 인사드리겠습니다. 또 말씀 주신 것처럼 피지컬 AI 모멘텀에 서 있는 지금 산학연 협력을 통해서 이 대한민국이 세계를 또 선도하는 미래를 함께 소망해 보도록 하겠습니다. 자, 이어서 황정아 더불어민주당 국회의원님의 축사가 있겠는데요. 황정아 의원님은 물리학자이자 우주과학 분야 전문가로 국회에서 대한민국의 과학기술 발전과 미래 성장 동력 확보를 위해 활발한 의정 활동을 펼쳐오고 계십니다. 자, 그럼 황정아 의원님을 큰 박수와 함께 단상으로 모시도록 하겠습니다.
네, 안녕하십니까. 대전 유성을 황정아 국회의원입니다. 스트롱코리아 2016 개최를 진심으로 축하드리고 오늘 행사를 주최해 주신 한국경제신문의 조일훈 대표이사님 그리고 과기정통부의 류재명 제2차관님을 비롯해서 관계자 여러분들께 진심으로 감사드립니다. 매우 시의적절하게 피지컬 AI 그리고 반도체 그 변곡점 그 시점에서 시의적절한 포럼을 개최해 주셔서 진심으로 감사드리고요. 이재명 정부는 AI 3강, 과학기술 5대 강국을 목표로 하고 있습니다. 대한민국이 원래도 반도체 강국, 메모리 강국, 그리고 제조 강국이었기 때문에 피지컬 AI 관련해서는 우리가 1강을 할 수도 있을 것 같다는 생각이 듭니다. 그래서 오늘 기조연설을 맡아주시고 그리고 연설을 해주신, 강연을 해주신 이종호 교수님 그리고 김정우 교수님 비롯해서 많은 전문가 여러분들께 진심으로 감사를 드리고요. 저는 더불어민주당의 과학기술혁신특별위원회 위원장을 맡고 있고 그리고 AI 강국위원회 간사를 맡고 있습니다. 그래서 최근에 피지컬 AI 지원을 위한 피지컬 AI 지원 특별법을 대표 발의한 바가 있고요. 그리고 사실 AI 3강을 가기 위해서는 많은 일들이 준비가 되어야 되는데 세상에 없던 길을 만드는 길이라서 아까 유재명 작가님께서 말씀하셨지만 좋은 AI 모델을 만들기 위해서는 좋은 데이터가 필요합니다. 그래서 모든 AI 모델에 지금 합법적인 데이터를 쓰도록 하기 위해서 국가의 자원이 들어간 모든 데이터를 국가가 표준화하고 관리할 수 있는 국가연구데이터법을 제가 대표 발의했고 이미 본회의를 통과했습니다. 여러분들께서 어떤 모델을 만들 때 의료 모델을 만들거나 국방 모델을 만들 때 항상 데이터를 구하는 게 굉장히 큰일이거든요. 그래서 그 데이터를 합법적인 수준에서 여러분들께서 만드실 수 있도록 하는 법안이 이미 본회의를 통과했고 그리고 AI 3강의 가장 심장이라고 할 수 있는 AI 데이터 센터 구축을 위한 특별법, AI 데이터 센터법 그리고 지산지소 원칙을 반영한 분산에너지 특별법 그러니까 AI 데이터 센터의 핵심은 사실상 전력이라고 생각하고 있습니다. 지산지수를 구현할 수 있는 법안을 제가 대표 발의를 했고 이 법안도 이미 본회의를 통과했습니다. 그리고 사실 AI의 문제는 근원적으로 에너지의 문제라고 생각해 왔기 때문에 에너지 문제를 해결하기 위해서 SMR을 지원하는 SMR 특별법도 제가 대표 발의를 했고 이미 본회의를 통과했습니다. 다양한 방면으로 우리가 가보지 못한 처음 가는 길을 만들기 위해서 속도감 있게 이 법을 추진하고 있고요. 그리고 이 포럼이 벌써 14회째를 맡고 있다고 하니 한국경제신문에서 과학기술 강국 도약을 위해서 지금까지 제시해준 비전과 설계에 매우 감사하게 생각합니다. 그리고 이 자리에 계신 모든 경제계, 산업계, 연구계 전문가분들께서 과학기술 강국 도약을 목표로 해서 이렇게 많은 해안을 나누어 주셔서 감사하게 생각하고요. 다 같이 힘을 모아서 과학기술 강국 대한민국을 다시 한번 도약하게 만들었으면 좋겠습니다. 저는 마지막에 이 포럼이 방점이 지금 물리학으로 돌아가는 것도 매우 반갑게 생각합니다. 항상 많은 분들이 최첨단의 이야기를 하고 있죠. 지금 눈만 뜨면 세상이 바뀌는 세상에 살고 있는데 그러나 항상 제일 중요한 건 기본이라고 생각하고 있습니다. 제가 물리학과를 졸업해서 하는 말씀은 아니에요. 그렇지만 어쨌든 기초부터 튼튼해야 된다고 생각하고 모든 학문의 기본이라고 생각하고 있습니다. 그래서 제가 대표 발의한 법안 중에 국가 총 예산의 5%를 확정적으로 과학기술 R&D에 투자하는 법안을 대표 발의를 했고 그리고 과학기술 R&D 중에서 기초과학 분야의 10%를 확정적으로 투입하는 법안을 대표 발의한 바가 있습니다. 아무리 잎이 많아도 뿌리가 튼튼하지 않으면 흔들리는 법이라 기초가 튼튼한, 기반이 튼튼한 대한민국이었으면 좋겠습니다. 저는 여러분들이 하시는 일을 과학기술정보방송통신위원회 위원으로서 국회 예결위 위원으로서 국회에서 입법과 예산과 정책으로 뒷받침하도록 하겠습니다. 스트롱코리아 오늘 포럼 2026년 정말 축하드리고 다시 한번 준비해 주신 모든 분들께 감사드립니다. 감사합니다.
네, 축하 말씀 전해주신 황정아 의원님께 감사 인사 드리겠습니다. 또 우리가 논의하는 이 모든 것은 또 세상에 없는 것을 만드는 길이라고 하셨습니다. 또 오늘 포럼에서 얻는 이 인사이트가 그 길을 걷는 원동력이 되기를 함께 소망해 보겠습니다. 기조연설은 AI가 지구를 넘어 우주의 무한한 데이터와 결합하며 만들어낼 새로운 산업 생태계와 또 기술적 가능성을 조망하는 시간 마련해 보았는데요. 딜런 테일러 보이저테크놀로지스 회장께서 지구에서 궤도로 AI의 새로운 스페이스 프런티어를 주제로 강연해 주시겠습니다.
We like to say in English, space is the place, but I will also start by saying space is just the beginning. I ask that you hold these words in your mind, not as a slogan, but as a technical argument. Because by the time I finish my remarks, I hope that you will agree that those 5 words are the most precise description of where we are right now. We are living through the most important transition in the history of computing. AI is leaving the data center, and it is moving into the physical world. It's moving into robotics. It's excitingly moving into autonomous satellites. It's moving into surgical systems. It's moving into 6G base stations. And it's moving into missile defense systems, among many other systems. We call this physical AI, and physical AI does not just need software. It needs a new generation of semiconductors that can perceive, decide, and act at a millisecond speed in harsh environments without a cloud connection. The performance bar is categorically higher, and the material science required to meet this does not yet exist at the scale the world needs. So let me start at the atomic level, literally. When you grow a semiconductor crystal, the foundational act of all advanced chip manufacturing, gravity is working against you. Heavier elements settle, convection currents disrupt the lattice, microscopic defects get baked into the material before a single wafer is cut, before a single transistor is laid, before a single chip goes to work inside a robot or a satellite. No clean room eliminates this. No lithography process fixes this. No downstream engineering reverses it. The problem is truly upstream. The problem is gravity. So the logical question is, what happens when you remove gravity from the equation? The answer has been accumulating aboard the International Space Station for 25 years, and it's unambiguous. 86% of crystal growth experiments on the space station showed an improvement in at least one critical metric: size, uniformity, purity, or device performance. 25 years, dozens of materials, the data is not in dispute. In fact, Voyager, the company I run, holds a patent for extraterrestrial manufacturing, a method that produces larger, more ordered crystals for high-performance optical communications, the backbone of data centers and the AI-driven global economy. This is not a concept. It's on orbit now. And so let's think about what the big picture implication of that. The global semiconductor market will hit $1 trillion by 2027, largely driven by AI demand. So the constraint is really not capital, and it's not imagination. It's the physics of growing crystals under a gravitational field. Space removes that constraint. So let's discuss why physical AI demands require a new material science. I think everyone in this room has been watching the AI wave and the build of the next generation data center. GPU clusters, hyperscaler CapEx, inference chips, that AI wave is real. But it's not the next wave. The next wave is physical AI, AI that leaves the server room and moves into the physical world. It moves into robots, it moves into autonomous satellites, 6G base stations, surgical systems, and missile defense systems. It moves into devices that must perceive, decide, and act in real environments in real time without a cloud connection behind them. And you can already see this transition in the data itself. CPU demand per GPU is rising, a signal that the architecture is shifting from pure compute to systems that must coordinate with the physical world. More CPUs per GPU means the more orchestration, more sensor integration, more real-time decision loops are required at the edge. The ratio is moving because the workload is moving. What's less obvious is the semiconductor gap that physical AI exposes. And I want to be very precise about where the gap actually is, because most people are looking for the gap in the wrong place. The challenge is not the inference chips. It is not a silicon problem. The AI accelerators, the GPUs, the NPUs, the inference ASICs, those are being designed and manufactured at remarkable speed. The industry knows how to do that. That is not the constraint. The constraint is everything around the silicon. The non-silicon semiconductors that physically AI and physical AI depends on. The components that have to make the system work in the real world, not in a temperature-controlled data center. Consider two examples. Power semiconductors, this is the silicon carbide and gallium nitride devices that regulate energy inside a robot, inside a satellite, inside a missile defense system. Those are not efficient enough. They waste energy as heat. They cap the performance envelope of every system they sit inside. And because they switch power at a high voltage and a high frequency in environments that silicon cannot survive, there is no silicon workaround. I want to repeat, there is no silicon workaround. You need better wide band gap materials, or you accept performance ceilings. The other example is sensors. The LiDAR arrays in autonomous vehicles, the radar front ends in satellite systems, the optical sensors in surgical robots, they do not see far enough on their current power budgets. Range, resolution, and power consumption are in direct tension. You cannot close that triangle with better software. You need better semiconductor materials at the front end of the sensor stack. This is the physical AI semiconductor gap, the material quality of the components that connect the AI to the physical world: power, sensing, communications, and control. The market for wide band gap semiconductors alone was $2.24 billion in 2023, and it is growing at 25% annually. The constraint is not capital. It is not engineering talent. It is the physical physics of growing high-purity semiconductor crystals in a gravitational field, a field that introduces defects into the material before a single wafer is cut. That is the upstream problem, and that is the problem that microgravity can solve. So now let's discuss the commercial low Earth orbit economy and the infrastructure being built now. I believe that the commercial LEO economy is the answer to Earth's materials ceiling. NASA's fiscal year 2026 budget includes $2.1 billion for commercial LEO development through 2030. This is deliberate construction of a new industrial sector in orbit. The question is, who builds it and who benefits from it? Let me walk through the platform, the ground ecosystem, and the proof that this economy is already real. The platform is Starlab, a joint venture with Airbus, Mitsubishi, MDA Space, Palantir, and Space Application Services. In February 2026, Starlab completed its commercial critical design review with NASA and entered into production. It will be delivered to orbit on a single launch, fully operational. Palantir's AI platform will run the station as a continuously intelligent, self-adjusting system, and companies like United Semiconductor have already reserved payload space for commercial scale microgravity semiconductor crystal production. The ground ecosystem is VISTA, America's first science park dedicated entirely to in-space research, 80 acres at The Ohio State University in Columbus, Ohio, tenants spanning AI, semiconductors, biopharma, robotics, agriculture technology, and biomedicine. NASA Glenn recently signed on, as did Yonsei University, giving Korea researchers reserved access to VISTA and the International Space Station. I also want to mention more proof that the Korean LEO economy is already real, and that is Space Lintech, the Seoul-based biopharmaceutical company contracts with Voyager as their mission management partner, pursuing automated protein crystallization and cell therapy experiments in microgravity. In January 2026, Voyager contracted with Space Lintech to manifest a new payload to the International Space Station, advancing microgravity-enabled drug discovery. Korean companies are not waiting for the commercial space economy, they are helping build it. And the institutional infrastructure is catching up. Korea established KESA, the Korea Aerospace Administration, to consolidate national space functions and accelerate commercial ecosystem development. In February 2026, the K-Space Forum launched with Hanwha Aerospace as a founding voice, bringing together KESA, KARI, private investors, and startups to build the framework that Korea needs to scale globally. Perigee Aerospace is also targeting its first orbital launch. SATREC initiative is supplying small satellite buses internationally. LigNex-1 is building defense-grade reconnaissance satellites. The Korean space ecosystem is not just a government program, but it has commercial ambitions. It is a commercial ecosystem with government backing, and that distinction matters a great deal for speed. Switching gears, NASA selected Voyager for its 7th private astronaut mission, Voyage 1, to the International Space Station, targeted for 2028. This is part of NASA's explicit strategy to transition low Earth orbit operations to the private sector and accelerate the orbital economy. This infrastructure is operational, the missions are booked, the economy is open, and now I want to tell you something additionally that should concentrate everyone's attention. For over 3 years, aboard China's Tiangong space station, scientists conducted a seemingly routine experiment, striking alloy particles suspended in a vacuum chamber with a laser, recording how they cooled and crystallized in microgravity. The equipment and samples were replaced 3 times. They kept going. The result, the world's first industrial-grade neodymium silicon alloy, solving 2 previously intractable manufacturing problems: slow crystal growth and brittleness, both the result of gravity-driven processes. What this enables is hypersonic flight. China did not discover this in a laboratory on Earth. They discovered it in orbit because gravity was the constraint and microgravity was the solution. Microgravity is a strategic resource. Let me repeat, microgravity is a strategic resource. The question for this room, for Korea, and for the allied Western and Eastern worlds, who controls access to microgravity? In fact, the technology stack that enables and makes space-based materials and research possible, edge AI, radiation-hardened electronics, autonomous processing, secure communications, is identical to the technology stack that makes modern missile defense possible. This is not a coincidence. This is physics. And I believe Korea knows this firsthand. Korea's low-altitude missile defense program, the Korean Iron Dome, was accelerated to 2029, 2 years ahead of schedule, approved, of course, as you all know, in April of this year. It is designed to intercept simultaneously low-altitude attacks at higher target density than Israel's Iron Dome, artillery shells, rockets, and low-altitude missiles from adversaries. Total investment, 842 billion won through 2030, and the Hanwha systems radar at the heart of it must detect and track hundreds of incoming target simulations. Those program requirements map exactly onto the physical AI semiconductor stack. Edge AI, inference at a millisecond of latency for real-time decision-making. Radiation-tolerant processors for survivability in a contested environment. High bandwidth tactical communications for sensor fusion. Autonomous engagement frameworks operating faster than human command and control. All of these systems engage in frameworks operating at faster than human command and control. These are the same problems as commercial space economy are tackling, but with much higher stakes. Think about what that means structurally. The silicon carbide and gallium nitride devices that power a humanoid robot's motor controller are the same material class that manages high voltage switching in a missile interceptor guidance system. The radiation-hardened edge AI processors that run a microgravity manufacturing module on Starlab is the same architecture required for autonomous engagement, logic, and a military vehicle moving at Mach 10. The supply chain is shared, the physics is shared, the strategic exposure is shared. If an adversary controls the production of wide band gap semiconductors at scale, including through orbital manufacturing, they do not merely have a materials advantage, they have a defense advantage. This is why the Korea-US alliance has a materials dimension that has never been explicitly named until now. Korea designs and manufactures some of the most advanced memory semiconductors on Earth. The United States is building the world's most ambitious space-enabled missile defense architecture. Both depend on the next generation of wide bandgap semiconductors. Both face a supply chain that is inadequate at scale. And both face an adversary who has spent 3 years quietly solving that problem in orbit. The commercial LEO economy is not a science project adjacent to these strategic realities. It is the solution, building an allied orbital manufacturing capacity as much as a defense investment as it is a commercial investment. These two cannot be separated, nor should they be. Golden Dome is the American system of systems equivalent, distributed, space-enabled, designed to sense, decide, and intercept at every altitude, from low-altitude artillery and drones to hypersonic glide vehicles traveling at Mach 20. It's projected to cost $185 billion. Voyager's role is as a neo-prime, full-stack enabler, solid, controllable propulsion, in-space maneuvering with electric propulsion, radiation-hardened digital avionics, command and data handling, AI and machine learning guidance, and RF and laser communications. It is not enough to have sensors You need architecture level intelligence where AI is intrinsic, distributed across every layer of the chain. Future missile defense will rely on edge intelligence across satellites, interceptors, airborne systems, and maritime sensors. Every one of those layers requires wide bandgap semiconductors. So in closing, Korea is very much at the center of this story. Where Korea stands is as one of the principal architects of the physical AI era. The question that defines the next decade is, where does physical AI get made? At the materials level, at the atomic level, where the physics actually happens, and as you heard today, I believe strongly that that will happen in orbit. The countries and companies that understand that fact first, that treat microgravity not as a curiosity, but as a production environment, will hold an advantage that no amount of downstream engineering can close. Korea has built two of the world's most important technology industries from that exact insight. That you do not compete on existing terrain. You find the terrain where the physics favors you, and that is what's happened in memory, and that is what has happened in displays, both pioneered by Korea. Physical AI demands better semiconductors, and better semiconductors demand microgravity. Microgravity at an allied commercial scale demands a permanent platform. That platform demands global ecosystems of builders willing to reach for it. And that ecosystem is VISTA, that platform is Starlab, and that partnership very much starts here. The singularity this forum is named for is not a moment of disruption. It is a moment of convergence. Let me repeat. It is a moment of convergence where physics, material science, AIs, sensors, 6G, and commercial space all become one integrated system. China has shown the world what that convergence produces in orbit. And the question now is who builds the allied infrastructure to answer that? In closing, Voyager is building that infrastructure, and Korea is exactly the kind of partner that this infrastructure is built for. I thank you very much.
자, 지금부터 여러분께서 실시간 질의응답 시스템을 통해 올려주신 질문들을 제가 대신하여 전달하도록 하겠습니다. 자, 첫 번째 질문입니다. 딜런 테일러 분께 또 질문 드리겠는데요. 중국이 텐궁 우주 정거장을 이용해서 우주 경제에서 선점을 노리고 있다고 하셨습니다. 중국의 우주 경제 수준은 어느 정도인지 더 많은 사례를 통해 추가 설명을 해줄 수 있으십니까? 중국의 기술은 미국과 그동안 그 동맹 진영과 비교하면 어느 정도 수준인가요? 이에 대한 답변 부탁드리겠습니다.
Yes, so the question of China, I would say over the last 10 years, the Chinese space program has done much to catch up with the US and its allies in a couple of dimensions. One is in heavy launch capability to orbit. This is something that they have improved dramatically on. They don't necessarily have the same safety factors that other countries have, so I would say much improvement there. The space station has been, I would say, a success. It is more modern than the International Space Station. Of course, it's only been in orbit for a few years. I think notably, every astronaut who has served on the Chinese space station has been active duty military. I think that's important for people to understand. And it has essentially the same research capacity physically to the International Space Station today, but with a more modern platform. This is why it's really important that the commercial space stations that will be coming online in the next few years get built, that they have the capability at least as good as the Chinese space station, if not more, and that we have global partnerships because I think ultimately what the people in this room do better than anybody in the world, together with folks in the United States, is lead in innovation, lead in perseverance, lead in tenacity, lead in creativity. And these things are the important ingredients in order to stay ahead of the technological curve, which I think will be extremely important going forward. So, notwithstanding my remarks, I'm very optimistic. I think that we have the right technology and the right partnerships. We can't take it for granted. We need to work together. But I am confident we will remain ahead of China in space for the foreseeable future if we implement the things that I talked about before.
Thank you very much. 자, 두 번째 질문으로 넘어가도록 하겠습니다. 자, 두 번째 질문은요. 스타랩 우주 정거장 프로젝트에 팔란티어가 참여하고 있는데 AI가 스타랩 운영에 어떻게 적용되고 있는지 이에 대한 답변 부탁드리겠습니다.
Yeah, it's a very good question. There's really two ways AI is employed by Palantir in Starlab. One is in supply chain optimization. In fact, when we first brought Palantir into the project, it was after a very successful optimization that they had done for Airbus within their aircraft supply chain. So part of it is on the supply chain side. The second part is with autonomous action. So one of the issues with the International Space Station today is it's aging. It requires quite a bit of maintenance. The idea with the next generation commercial space stations, whether it's lab space or whether it's the functioning of the space station itself, is that you have less hand-holding, less maintenance, and more autonomy. And to do that, you need intelligent systems that are low latency and have intelligence at the edge so they can survey what's happening and make adjustments based upon that. So that's the second area that Palantir is helping with. And I should also mention, within Voyager itself, we have several AI initiatives putting more intelligence directly into the chips and ASICs that will go on the station as well.
Thank you very much. Here's our next question. 자, 세 번째 질문입니다. 소재 분야에서 우주 제조의 장점이 크지만 지구 생산과 비교하면 여전히 비용이 비쌀 것 같습니다. 스페이스 X 등 발사체 상용화로 비용이 줄어든 상황에서 회장님이 생각하시는 구체적인 우주 제조 비용은 어느 정도인가요? 그리고 스타트업이 아닌 우리가 아는 대형 기업들도 또 우주 제조에 나설 수 있다고 보시나요? 있다면 어떤 곳들일까요? 이에 대한 답변 부탁드리겠습니다.
It's a very good question. I would say two things. When you think about manufacturing, whether it's here on Earth or in space, pretty much everything is derivative of power, right? Power is absolutely critical. Of course, you have unlimited solar in space, but harnessing that is the real challenge. I think there's an opportunity not only in LEO, with the constellations that will be built out for orbital data centers, to leverage that innovation on the power and form factor to do in-space manufacturing. So I'm very excited about that. The other thing I did not talk about in my remarks, but is a very exciting development, is the lunar environment. We, the US and its allies, are returning to the moon. The moon provides some really interesting opportunities because there's not only resources in situ, but there's the opportunity to install permanent power, whether that's distributed solar or whether it's nuclear power. And I think that could really open up the aperture for in-space manufacturing as well. You're not getting purely the microgravity that I referred to earlier, but you are getting some of the benefits. In terms of industries, semiconductors, as we've already talked about, biopharma is extremely interesting, not only for drug development, but also working out drug formulations. Ag tech and innovations around ag tech are quite interesting as well. And then, of course, as I mentioned previously, anything to do with orbital compute. You can imagine having something intelligent in space that's able to replicate itself. That's kind of the holy grail of next steps within space manufacturing. I think Elon has talked about having a mass driver on the moon where you're actually putting things back in space after utilizing the resources in situ. So it's incredibly exciting, and I want to emphasize VISTA that I mentioned earlier. There's now 18, I believe, global universities as part of this consortium. They all have these research areas, many of which are present here in Korea. And as we all know, in these research areas, at the leading edge of innovation, is where a lot of these opportunities are first identified. And then having a model that rapidly scales these innovations and puts them in place in commercial platforms, I think, back to the China question, is one way that we stay ahead on the innovation curve. So I'm extremely excited about it. I think Korea is very, very well situated, given the capabilities in this country, to take advantage of in-space manufacturing.
Thank you for your answer. So we are moving on to our next question. Our next question is in English. So, as China is developing microgravity for new tech brought through in the space, what can South Korean companies and US partners work together on to compete with China from near and midterm perspective? Yes, so could you give me an answer? Give us.
Yeah, so I think it goes back to what I said earlier. I think part of solving a problem is asking the right question, right? And one thing I'm very impressed by with what's happening in Korea right now, and it's not only people I meet with in the government, what I see the focus areas are, but it's also the commercial partners that I've met with, is these questions are being asked. And so I go back to rapid innovation with research and development, leading to commercial partnerships, leading to commercial platforms. Right, this flywheel is the key to success, and I think I see strong evidence, I'm using that word strong, I see strong evidence that Korea is understanding that flywheel. So I'm actually very optimistic, as I said earlier, but I think the key thing is innovation leading to commercialization, leading to commercial platforms. That entire chain, you can't skip any of those steps, right? You can't have a commercial platform without the innovation. You can't have the innovation without the commercial partnerships. You can't have commercial partnerships without a commercial platform. So all three of these things are really critical, in my view.
Thank you so much. Here's our last question. 네, 스타랩의 반도체 결정 생산용 공간이 예약됐는데 실제 상업 양산은 언제쯤일까요? 그리고 일반인이 쓰는 기기에 우주에서 만든 반도체가 실제로 들어가는 시점은 현실적으로 언제쯤으로 보시나요? 이에 대한 답변 부탁드리겠습니다.
Well, let's see. In terms of the very last question first, when will we see commercial production of semiconductors and consumer products? I think that's a ways away. At least 10 plus years. However, between now and then, there is a big ramp up. And I think that ramp up will start as soon as the commercial space stations come online. As I mentioned, we already have semiconductor capacity booked on Starlab. We're actually at about 140% of our capacity pre-reserved on Starlab already. So you ask yourself, okay, well, why not build a second Starlab? Good question. I think we will. But I think ultimately what will happen is as these commercial space stations come online and the innovators understand the magic of microgravity, you'll have these commercial space stations be a big success. Korea will be involved in that, I'm sure. I have no doubt. Then what I think will happen, and it's sort of embedded in the question, is we will have special purpose platforms. One for semiconductor manufacturing, one for biopharma, one for drug manufacturing, one for data science. So I think that's ultimately, just like we have here on Earth, you might have a special purpose building at a university with a lot of different innovation happening, but once something reaches scale, it moves out of the laboratory into its own dedicated facility. I think that's going to be a very similar model in space. So I think this will all happen in the late 2020s. And then I think there'll be a rapid scale up. But don't forget the moon. I think a lot of this will happen on the moon as well.
Thank you very much. Thank you for your valuable insight today. 자, 이것으로 기조연설 모두 마무리하도록 하겠습니다. 수고해주신 딜런 테일러 회장님께 다시 한번 뜨거운 박수 부탁드리겠습니다.